All right, welcome to This Explainer. Today, we are unpacking an incredibly compelling academic report by Ezekiel Arome, and it tackles what is honestly one of the biggest paradoxes in modern cybersecurity. Think about it. How do you train a unified, highly accurate network threat detector across entirely different organizations without ever sharing the raw, sensitive data? Usually, asking companies to share their raw network traffic is literally like asking for the keys to the vault. It's just not going to happen, right? But as we'll see, it's totally achievable through a brilliant application of federated learning. So let's jump right in.
Here is our roadmap for the breakdown. We're going to cover the cybersecurity data dilemma, look at the federated system architecture, the FedAV algorithm sequence, model design and hyperparameters, global convergence results, and wrap up with the confusion matrix analysis.
Starting off with Section 1, the cybersecurity data dilemma.
So, the underlying reality here is that modern intrusion detection systems absolutely thrive on diverse data. The more threat variations a system sees, the better it gets. But here's the catch. Legal barriers, strict privacy laws, competitive isolation, all of this makes centralizing that raw network traffic virtually impossible. You simply can't ask three distinct organizations to just hand over their raw packet captures to a central server. No way. And that is exactly where federated learning steps in as a massive game changer. Instead of pulling the raw data, federated learning leaves the raw traffic firmly locked on premises, and it only shares the learned mathematical weights.
Moving to Section 2, let's check out the actual federated system architecture.
This illustrates how the topology actually shakes out using the Flower framework. Notice at the top, we've got a single aggregation server, and it's coordinating three completely independent clients down below. Now, a crucial requirement for this research was that every node had to use the exact same algorithm. So all three clients are running the identical artificial neural network architecture, and they're communicating with the central server via gRPC on port 8080.
But pay close attention to the data each client holds. It is highly heterogeneous. Client 1 holds legacy DARPA-derived traffic. Client 2 has modern enterprise traffic, complete with DOS and brute force scenarios. And Client 3, that one's packed with IoT-specific attack traces. This perfectly mirrors realistic, messy conditions across a network where data is just not uniform. In data science, we call this non-IID, or data that is not independent and identically distributed. Trying to federate across three completely different benchmarks like this simultaneously, it's a huge challenge, and frankly, it's what makes the success of this system so impressive.
Okay, Section 3, the FedAV algorithm sequence.
This is basically our map. It's the Federated Averaging Strategy, or FedAV, which is the baseline strategy for centralized federated learning. It maps out the exact flow of weights back and forth between the server and those local clients over a single communication round. To simplify that sequence, we can really distill the heartbeat of this entire system down into three main phases. First up, the server initializes and broadcasts the global model weights out to all three clients. Second, those clients take those exact weights and train them locally for 2 epochs on their own private, raw data. And third, the clients send those freshly updated weights back up to the server. The server then aggregates them, but crucially, it weights them based on how many local samples each client actually has.
Let's move on to Section 4, model design and hyperparameters.
So, before we get to the results, we have to look under the hood. The researcher made some very deliberate design choices here. Take the hidden layers, for instance. There are only 3. Why? Well, they empirically found this is completely sufficient for tabular intrusion detection data. Going any deeper would just cause overfitting and bog down communication. They also set the local training epochs to exactly 2, which strikes this perfect balance between keeping communication efficient and preventing the client models from diverging too far apart. And the whole process is capped at 10 federated rounds as a safety margin, just after hitting a solid plateau.
I actually want to pause here for a second, because handling that non-IID data we talked about earlier, that is the absolute biggest hurdle in this whole experiment. Since each client's network traffic looks completely different, the mathematical weights they send back up to the server can really clash. And that's exactly why techniques like applying batch normalization after each dense layer and using the Atom Optimizer with its adaptive learning rates are so essential. They basically act as shock absorbers, stabilizing those wild, varying client distributions during training.
All right, Section 5, global convergence results.
With the system built and the parameters set, the proof is really in the data. Looking at the global model evaluated on a massive 16,600 sample held-out test set, watch how rapidly the global accuracy, that's the blue line, just shoots straight up to 99.4% by round 10, while the red loss line totally plummets.
Meanwhile, you can see how the central server manages to rein in and stabilize the slight accuracy variations happening during the local client training. There are some seriously fascinating insights to pull from this. First off, the model hits 94.6% accuracy after just one single aggregation round. That kind of speed is possible because the researcher harmonized all those diverse data sets into a shared 40-feature space beforehand. But, it wasn't perfectly smooth sailing. Notice that little loss spike right around round 9? That is actually a very well-known instability of the FedAV algorithm when it's dealing with non-IID data. It's called client drift, but it recovers beautifully by round 10. Also, Client 2 struggled a bit more locally. Why? Because 80% of its data was benign enterprise traffic. That made the rare attack classes much harder for its local network to learn, at least until the global aggregation stepped in to save the day.
Finally, let's wrap up with Section 6, Confusion Matrix Analysis.
This confusion matrix is the ultimate proof of the system's success, breaking down the actual predictive performance class by class. It boasts a staggering 99.44% global accuracy across the entire held-out test set. If you trace down that dark blue diagonal line, you're seeing the system correctly nailing massive amounts of benign traffic, DOS attacks, and network probes with practically zero confusion on the outside grid.
And the performance breakdown shows us exactly why the numbers are so good. The macro F1 score actually outperforms the weighted F1 score, which is a huge win. It means the model is treating every class equally. It isn't just relying on the sheer volume of benign data to artificially inflate its score. In fact, for minority attacks like brute force and exfiltration, it hits a perfect 100% F1 score. The network spots them easily. The only real hurdle left is the boundary between benign traffic and denial of service or DOS attacks. There were 69 false negatives, where benign traffic got flagged as DOS. But that makes sense, right? Because a DOS attack literally functions by mimicking peak benign traffic volumes, making it incredibly tricky for the detector to tell them apart.
So as we wrap up this explainer, the performance we've looked at today proves something absolutely vital for the future of cybersecurity. Maintaining absolute data sovereignty does not mean you have to sacrifice detection accuracy. By leveraging federated learning, completely separate organizations can team up to build a world-class threat detector without ever showing their cards to each other. But it does leave us with one incredibly exciting question for future research. Can we take this out of the simulated lab environment and plug this exact framework directly into a real-time live network packet capture pipeline? It's a thrilling prospect for sure. Thanks for hanging out and exploring this with us.